Hello everyone and welcome back. So now that we've taken a look at Perlin Noise 2D, it's time to move over to Perlin Noise 3D, and we're going to do this all in one video, starting out with a little bit of theory and then moving into the implementation itself. Lee?
All right. Yeah, as Jason said, we had slated a couple of videos for this, but we've looked at it and go, there's not much theory to it. It's like going, we've already discussed most of the theory that is involved with Perlin noise. And if I can get over to Firefox real quick and bring up my handy dandy paper on noise that I really enjoy. You need to read this. If you're curious about noise, read this. It's good information. But we discussed the theory behind the 2D noise on how we take a randomly or pseudo-randomly rotated gradient and then we overlay them over top of each other and get the resulting grayscale color at the point where we're sampling. And then we apply that as our value for the noise at that location. Now, with 3D, it's just the same thing times two. Instead of having 4 corners for a 2D plane, we have 8 corners for a 3D cube. We're still going to be using the same 12 vectors that we defined for our unit cube going to the midpoint of each edge. These will define the random orientations for our gradients, but the calculation will be slightly more complicated, just like it was in value noise. With value noise, we sampled the 4 corners, and then when we moved it up to 3D, we sampled 8 different points, and then we had to do some additional blending between each of the new points that we brought in. Same principle here with Perlin. Nothing's going to change there. As far as theory, that's pretty much all there is to it, which is why we're going to keep this one short and combined it with the code.
Implementation.
Yep, the implementation, because the implementation is almost as easy. Because we're going to start with our Perlin 2D implementation, which is all this code right here. Copy it. And paste it. And we need to make a couple of changes. Because it's 3D, we need to take care of getting our argument for our third axis, which will be Z or Z for you people who prefer Z. We're going to bring in another variable. This one we'll call K. This will be the floor of Z. We're going to get the whole number or the fractional component of Z by taking our Z and subtracting it by K. And just like before, where floor is returning the whole number or the low whole number variable component of our whole number or our real number into K. So now we've got an integer. We subtract that integer from our real number, which results us in our fractional component. And then we need to make sure that we do not exceed 255 by masking it with 255. And inside of here, we'll have to make some changes. We're going to be renaming a couple of these. We're going to add in a third part. This last L is going to represent whether or not we're using the low value or the high value of our Z unit square. So I'm going to change each one of these 4 to hold the low
Lows.
part. Yep, the lows. And then I'm just refactoring as I go along so I don't have to type it everywhere else throughout here. Now, inside of our indexing for our lookup inside of the permutation table, we have to take into consideration the z-axis. So we'll do that by adding in what gets returned by the perm lookup of the k element. And then I can copy this and paste it in each one of our values. So now each one of these are taking in the z-axis. And for some reason it is not happy. Why are you not happy? Because I did not put the last one in. There we go. All right, now this handles all of our low our lower sample points, the lower corners in the z-axis. So we have to sample the 4 upper corners in the z-axis. So I'm going to copy these 4, paste them again, and change the third L to an H for high. And then we're going to add 1 to our index for the lookup for the K element. So that will take care of those. Now inside of here, we're going to do pretty much the same thing that we did up here by adding another L and then refactoring in the name change. So do this a couple of times. Whoops. And then we have to take in consideration our z-axis. And this has to be, change these to vector 3s. Because now we have 3 axes to deal with, we need vector 3s.
And one more set of changes over to the right and left just a tad. Look for the word vector 2.
Yeah, there it is. Because we need 3 components. So because these are all the low points, we don't need to add or subtract anything from these. So we'll just add Z or Z. I could never get the hang of just saying Z.
I just say Z.
All right. Now we're duplicating all of these, and we're going to change the last L to H just like we did in the last set of variables. And over here, we'll subtract 1 from each one of these. And we're subtracting instead of adding because we're just controlling the direction that the vector is pointing. So if we were to add, we'd be pointing in one direction. By subtracting, we're just reversing the direction we're pointing. And we need to get a third gradient, which we'll call W. And this will be the result of fade casted down to a float. And we will send Z into the fade. That will get our third part. And then we'll need to change these up a little bit. Because we're going to have to do a total of 7 different lerps now, because we are, well, I'm having a hard time getting that, because now that we're dealing with 8 different corners, we'll have to do a few more lerps. All right, so this one will be, well, I'm trying to remember the order of these. So this will be NXLH. So these will be all lows. This will be high. And this one will be And I'm typing them wrong. Am I? No. All right, I got them. They're here. This one's needs the low. There we go. So basically, we're going from x being low to x being high for both of these, but this will be with z set to low, and this one will be z with high. And we'll do the same thing again. So we'll duplicate these. And these will be with the y component set to their high counterparts. I'm getting hung up with my mic cord. You probably could hear a little bit of scraping. That's what it was. All right, so that'll take care of those. Now this is just the first set. I can duplicate these. And these will be NXYs. So we'll be going from this one to this one. Oh, let's write this one. And from this one to this one. And then from here to here. This one will have all of them. And we'll have to come back and adjust. The first four we're adjusting by our U gradient. The second two are adjusted by the V gradient. And then the last one is by the Z gradient.
Z?
Yeah, Z, as opposed to Z. Or, sorry, W.
Thank you.
Yeah, technicality. It's a letter, right?
It's all
that
good.
Counts. I know. All right, so we build it. Everything seems to build out fine. So if we go over to Game Manager, if we look at our noise, let's copy this one. We can paste it in, comment out this, comment out that one, and we need to add in
Our iteration.
Yep. So we can test to make sure that we get some animation on it. All right, let's see what we've got set for our frame rate. That should be fine. Build it, no errors.
A quarter of a second, you think?
Well, these are running in millisecond, or like, what's this one? I think about 60 milliseconds. So it should be fine. We'll find out though. What's the worst that could happen? I could blow it up. So we play it. Yeah, look at that. 56 milliseconds.
Mm-hmm.
So now with our 3D noise, you should be seeing some nice smooth animation as it goes from state to state.
Then we get a really big jump in there.
Are we? Okay.
Yes. We get nice, smooth looking, then all of a sudden it's a giant jump, and the whole thing
is shifting.
Yeah.
All right, so it's not going to help if I switch over to my editor. All right, so if I go back over in the code, so iterations is incrementing by 0.01. Or 0.1, not 0.01. And see if I'm missing anything up in here.
Well, let me go ahead and hit pause real quick so
Pause.
that you could peruse through all of this.
Okay.
All right. Okay, Lee, it's back to you.
All right. Well, after hours and hours of excruciatingly going
Whatever.
line by line, okay, maybe about 30 seconds, realized that we forgot to change these over to point to
Highs.
our highs instead of low. When we just duplicated our low samples instead of the high sample points, which was the cause of the whole problem. So
All right,
if we
let's
hit
see.
play now, then we should get a nice smoothing changing gradient. So, and this one does seem to have some nice things about it. We don't have that little black splotch in the corner. And I haven't noticed any, well, yeah, there is still a little bit of
Yeah, it's
lines coming
there.
in.
It is
Yeah,
definitely
it is there.
it's
So it's
definitely
got
the
to be the
nicest.
tables.
I was just going to say it's definitely the nicest looking animation of the three.
Well, nobody knows yet because I haven't seen the third one yet.
No,
Only we've seen that one.
that's true.
Yeah,
But
so out of the two we've done, this is the better looking
yeah,
of the
this
two.
looks very nice. Very nice animation.
So, but it's all going to be a trade-off of what you're going for, how much performance that you're going to need out of it. So that's always going to be a deciding factor on what kind of noise that you use.
Mm-hmm.
So if you don't need something that has to be rendered, once every second, then Perlin noise might do it for you. If you need something that is faster, but you're willing to sacrifice a bit of quality and the animation and the overall look of it, then you might want to look at value or simplex. It's all based off of your needs. But I don't know. It's like you want to play with this one a little bit, or do you want to do that and do some comparisons in the next video?
Yeah, I mean, what is it that you want to play with? I mean, because we can just go
Well,
ahead and do it all in one video.
okay. Well, what I was going to play with is I wanted to point something out.
So jump back over
Particularly
there real quick.
to where code.
Yeah, hang on. I'll do it real quick.
Okay.
So that was taking 0.58 milliseconds, right?
Well, 58 milliseconds.
Oh, okay. Wait a minute. So
58 milliseconds works out to
yeah,
1,000 milliseconds in a second.
right.
So 0.58 of a second.
Okay.
So if you wanted to go faster based on our speed, we could do 0.6.
Let's see if that actually works.
Okay. You just want to see how fast
Well,
we
you're
can create the
playing now,
animation?
so yeah, I'm just curious. That's what I was looking for, because it just seemed like if we had so much room to play with, ooh, that looks awesome.
I don't know. I can't tell with the lag on the update.
I'm sorry,
So,
but it looks really cool over here.
oh, does it?
Yeah, hopefully the
Kind of plasma looking?
Yep. That's very sweet looking. All right, that's what I was curious about, because it just seemed like we had so much room to turn it up, and my next question was going to be what was wrong with the problem of getting it to look a little bit more organic. Nice. Okay, now let's see what kind of things you wanted to play with.
Well, we did that. Well, let's see what happens if we take one of the noises that runs even faster. If I remember right, we can go to 0.3 and switch over to our value noise. So if we do the same thing with the value noise and compare and see which one looks nicer. This one's going to be running almost twice the speed, though.
That looks horrible.
Does it?
Yes.
Not bad.
It's all right. Slow it down and let's see if it's maybe it's just too fast right now, and that's what because that just looks horrible. Put it back to the same speed as the other one.
Okay.
wow, when it was slower, there's just
Well, we were running at 0.38, so I was trying to update it too fast. I think that was part of the problem that we're getting. We're
it
getting
almost
some
looks like
jumps in
just
it.
a fading slideshow.
On this one right now?
Yeah, slow it down some more. Where with the Perlin noise, with that one, it had a very nice looking. It was just a very nice, organic, constant, like a fluid type feel,
Right.
and that's not what I'm seeing here.
Well, you got to remember the difference between the two is Perlin, specifically the 3D, is based off of gradient noise,
Right.
which is why we're getting that nice smooth transition from place to place as opposed to value noise. So we get that nice convection type feel to it.
This just, to me, this one just looks like,
Like it's fading from one
yeah,
type of noise to a next.
yeah. And is that what? And because as I've already said at the very beginning, or maybe off camera, I don't know nothing about noise stuff. I always just use what's built in.
It's what is happening. You're lerping between different states, so you're generating noise at certain increments,
Mm-hmm.
and then you're blending from one to the next with
Right.
value noise. Where in your gradient noise, you're generating based off of that gradient, so you get a more smooth transition as you're rolling through it, which is why you get that nice convection feel to it.
Okay. Well, as long as this is what you were expecting to see, where the other one would feel like rolling clouds and all, this does not. It feels like one set of clouds blending over to another that's a little lighter, then blending over to another that's perhaps a little darker.
Right. I'm going to have to compare that with the simplex, because the simplex is also a gradient noise.
Okay.
So it should also have that convection feel to it.
Gotcha.
Now, we can also, one of the things that you can do is adjust the overall speed of the transition
Mm-hmm.
by adjusting your iterations. So right now, let's try that again with 0.6 at a
Points.
0.06.
Thank you.
And half the iteration, but let's do this based off of the Perlin noise.
Okay.
And the other thing I want to do.
Well, let's only introduce one thing at a time, so then come back and do the other.
Okay. Because I'm still going to be updating as fast as I can based off the texture size, but the rate at which the convection is happening has been cut in half. So it should run a bit smoother.
Yeah, it looks very organic, very smooth, very cool looking.
So if I pause that, or not pause it, but
Yeah,
stop
I
it.
love your idea of pause. Every time you say pause, you turn it off.
Well, I pausing my brain mentally.
Do your
is
kids
what's
scream
going
at you
on.
when you're in the middle of watching a TV show and you're like, "Here, I'm going to pause the show," and like on DVD, and you just like turn it off?
Yeah, I guess. I don't know. I've never really done that. That would probably be annoying, though, wouldn't it?
Probably. Okay, so what you doing now?
Well, what I want to do is I'm going to comment out the rest of this stuff.
Mm-hmm.
Oh, no, I can't do that because I don't have comment anymore.
I'll bring
But,
it back. I'll turn off the hotkey problem that we're getting from Camtasia.
All right, so I need my toolbars, text editor here. What I want to do is demonstrate the problem that we had with the Perlin 2D noise is still in existence even now. So if I take, let's copy this one. So if I take this and paste it, whoops, we still want var here. But if you remember where we had to divide by 2 to prevent the solid gray texture, not 0. All right, so if I switch over to our Perlin 3D implementation, bypassing our noise iterations, So if I run this now, we still have that same middle gray artifacting that we get because of the all zeros. Now, what you can do to fix that, or you can't really fix it, but the way we can get around it is if I uncomment this, inside of our noise, instead of looping from a start of 1, start at 2 and go to 9. So what we're doing is we're bypassing the solid gray sheet because there's no point in calculating the solid gray noise. It's not doing anything for us. So if we start at 2, we're automatically going to be starting off at that divide by 2 here. And then we're just adding 1 to the number of iterations that we're going through.
Okay.
So we'll be bypassing that middle gray. We'll also change the look of our overall noise a little bit too. So if I build that out, and then I go ahead and run it,
Yeah, it definitely changed the pattern that I was feeling earlier.
Yep. But all we're doing is getting rid of that solid gray layer. We'll still add another layer, which is why our time is still the same.
Right.
But instead of starting with 1, we're starting at 2 and going to 9. So we still have 8 octaves overall. Now, one of the things as well is we're basing all of our times off of 8 octaves of noise. There's nothing that says you have to use 8 octaves of noise.
Mm-hmm.
I could use, well, that would be 12. I could do, or that would be 11 octaves. I could use 12 octaves of noise if I could type. I'm going to bump this up to 0.1 now.
Okay.
Because this will be a few more octaves. So we get a little bit different pattern. There's a point of diminishing return now. So after a certain point, it's like going, yeah, I can add extra octaves of noise, but do you see it? Or do you really need it? And you can look, we've jumped up our render time to 83 milliseconds. Conversely, do you even need 8 octaves of noise? You may find that for what you're doing, let's go back down to 0.4. And if instead I decide I only want 4 octaves of noise, you may find that that meets your needs. And we've shaved off, a good 20 milliseconds off of our render time.
Yeah, it looks pretty cool too.
And for depending on what you're working with, even that might be overkill. So you could come back in here and go, okay, let's just do 2 octaves of noise.
Very cool.
And then if you look at our speed, we're down to 22 to 25 milliseconds.
Mm-hmm.
And for some purposes, this may be all you need.
What are we still at texture size of 128?
Yes.
Okay. Yeah, so now if you change the texture size down to 64 and leave it at, well, go back to 4, so you get 2, and then do your texture size at
1/4 the size, 64.
Yep, so this is going to blur it out a little bit.
Right, because we're getting upscaling
Yep.
based off of the size of our texture.
But I'm just curious what it's going to look like now with just 2 and that, because now your time's going to improve even more.
Right.
Ah, very nice. Look at that, 5 milliseconds too.
Right. So you might find that this gives you the effect that you want.
Mm-hmm.
And even then, if I was doing something like billowing smoke, I'd consider that too high detailed. So then maybe 24.
Living on the edge.
But if I wanted something like billowing smoke, that might work. And you're talking about less than a millisecond to render that.
Cool.
So it all depends on the effect you're going for. What kind of quality do you really need? Everything in your game doesn't need to be at 1024 by 1024. So you can get some really cool effects with really, really small textures.
Right.
But just for fun, though, and because we need to be fair. What does value noise in 3D look like and run like at 24 by 24?
Yeah, there goes that pulsing, shifting, pulsing, shifting.
It just doesn't give the same feel.
No, not at all. Not at all. And
but it's a whole lot faster. It's at 0 a lot more than it is at 1.
Well, that's irrelevant if it doesn't look good.
Yeah. This is true.
And again, I hate to ask, but this is how it's supposed to look.
It's in everything that I've seen. This is very typical of the results that we get. So, like I said, everything has its own unique feel. In my very first implementations, one of the things that you get is very squared off edges. When I was playing with one of my other little test projects, you were getting almost like straight lines across. But that was mostly because of the way the frequency was being calculated as well, which is something that we're not doing yet. Because one of the things that we're not really taking into consideration is frequency, how large the noise is going to be relative to our octaves. Right now, we're assuming that our octaves are controlling how big or small our noise patterns are, where later on that will be controlled by frequency.
Cool.
Then we end up looking at lucidity, I think it's called. I can never pronounce the word, but it's basically how much how concentrated the pattern is. Right now, if we look at our code inside of our temporary method, we are taking I and we're multiplying it by 2. This is this 2 is in effect the lucidity of our noise. It's the spacing in between a fractal, I think is the definition for it. But this is being controlled by this value. If I were to go, let's put this up to a power of 8. I'm going to switch back to our Perlin noise, pick on it for a little bit, because I'm going to be adjusting stuff and I don't know what my time frame is going to be. I'm going to go ahead and bump this back up to 0.25. I'm sure it's going to be more than I need, but I'm going to use, in this case, instead of a power of 8, though, I'm going to raise it to a power of 16, but I'm going to change our multiplier to be 5. So each iteration is going to have a larger difference between the last one. And make sure everything else is right. Built. And
there you go.
Yeah, it's running that. So what we get is a bit of a different pattern going through it. We've got a larger shifting on the gray in the back and then a mid noise, but we don't have that low noise like we were having before. So we're controlling the difference between the different levels of noise.
You sure? I just can't tell because of the resolution, I guess, that the texture's running at.
Okay, well, we can change that as well. Let's go back up to 128. So we've got some high res noise,
Mm-hmm.
and then we've got some mid level noise,
Mm-hmm.
and then we've got some really larger shifts in color.
Mm-hmm.
But it's only 3 different layers of noise.
Yeah.
Where we had a much finer shifting from high level than a little bit low, or we had a real high frequency noise, and then we had another noise that wasn't quite as high, but there was more layers being added in. That is controlled by the luminarity.
Okay.
So if I were to go back in, just because now that we're at the higher res, if I were to put it back to say 2
Mm-hmm.
and 8, just so we've got a bit of a comparison, you can see how it shifts the way the noise looks. So
Yeah.
now it doesn't have almost like in here this looks more like a uniformed cloud type
Mm-hmm.
um, pattern to it, where in the other one it almost looks like watercolor where you've got the water drip stains.
Mm-hmm.
And if I were to adjust that to make it even more prevalent, let's try to do say 24 by 10. So now you get large splotches of color, but the high frequency just dots it. So what we're doing is we're getting one really, really, our very first pattern
Looks like stained
of
glass.
noise. Yeah, at this point. But then we've got this larger patch in the background. And I believe that we're only getting maybe 2 or 3 layers on that. Because what's 2 to the 24? Calculator time. All right, so if we take 2, raise it to the 24th, all right, we get a fairly big number, and we're multiplying it by times equals 10. So how do I figure that one out? So each time is 10 times higher than the one before it. I have no idea how to calculate that right off the top of my head. But I'm going to double it. It's not as, because we're multiplying by 10, now by 20,
Mm-hmm.
we're getting even fewer shifts. So we get that high frequency noise, and then our background, our next layer is even larger. So the higher your luminarity is, the more spread in size you're going to get between each of the different octaves. So that's probably the best way you look at it. Each octave, the size of the noise is going to change by a greater amount between each octave.
Well,
By
leaving that, go ahead and hit stop and switch over, leaving everything set the way it is, back to the Perlin 3D. Curious on how that would look.
that is the Perlin.
Oh, I'm sorry. I thought you were
You
on
want to see what
value.
it looks like in
Yeah,
value?
yeah.
Boy, that really does bring out the blending between, doesn't it?
Yes, it does. Wow. Okay. Because looking at it, I was like, wow, finally it's starting to look kind of organic. I wonder what that would do for Perlin if it would look twice as organic. Then you were like, well, it's already Perlin.
Yeah, it's like, no,
Darn
we were
it.
playing with Perlin because Perlin looks cool. Now, this is part is considered the luminarity. Now, I can drop that back down to 2. there's another effect that we can play with, and that would be the persistence. And right now we have nothing considered, or no concept of persistence. What persistence is how much of a contribution each successive octave is going to have on the overall look. So
Well, quick
where,
question. Are we getting pretty far away from just Perlin Noise 3D, and this is something that should probably go towards the
well,
end? So as you make
yeah,
these adjustments, we can compare them with all three?
we could. We will actually have a couple of videos that will take the stuff that is, because right now we're doing all this inside of our update noise.
Mm-hmm.
But the stuff that we're doing here would be something that would be nice to be able to control for all of our noises. So it'd be nice to have all of our noises capable of controlling a bit more than what they've got now. I would like to be able to control and shift the frequency of our noise and control how many octaves of noise are we going to apply. What kind of persistence
Right.
is each octave going to have? What is the linearity of our noise? So it just gives us the ability to fine tune the noise that we're requesting, as opposed to forcing the programmer to, every time he calls our noise, to figure out, well, I need to make loops to control this many octaves, and if I want it to look this way, then I'm going to need to code this. So instead of having to force the coder to do that, it'd be nice that if we had methods that the coder could call and go, okay, I need noise that is six octaves in depth, has a persistence of 0.5, linearity of 2, and starts off with a frequency of 20. And then they could just call that, and what it returns back is what comes out of here. So all of this calculation that's coming back in, and we're building our texture, instead of doing this, they would end up with, in essence, this end value after it's run through all the iterations, done all the calculations, and then averaged them out. Then this comes back, and then our programmer can then use either that value alone, or they can do a loop through and populate their own texture.
Okay. I was just wondering. I just didn't want anybody to miss out on anything, and I felt like we were kind of getting a little bit further away from.
No, I think of
3D.
it as foreshadowing of some of the stuff that we're going to get into.
Okay.
So, and it would be kind of neat to even have a method later on where they go, okay, I need a texture of noise with these values that is 16 by 16 or 64 by 64.
Right.
And then the method just hands you back a texture and you go, thank you, and just go with it.
Yeah. Agreed. All right. Well, let's go ahead and call it on that one. And with that, we'll just say that's going to wrap up all of the Perlin noise, because I'll say that, we've got all the playing around put into this video as well, and that lets us move on to Simplex 2D noise next. So that will wrap up this video. Thanks a lot, everyone.